Because of its superior physical and mechanical properties, steel is one of the most important materials in use today. Steel exists in various forms which are characterized by each type's unique crystalline structure called microstructure. These structures include austenite, ferrite, pearlite, bayanite, and martensite. All of these possible microstructures can be formed by transformation during cooling from austenite. To form austenite, steel must first be heated approximately 850 to 900 degrees Celsius, 1,560 to 1,650 degrees Fahrenheit. This is the transformation temperature needed to produce the desired structure upon cooling. How much of these different microstructures form upon cooling depends on both time and temperature during the quenching sequence. Each of the different microstructures exhibits different physical and mechanical properties. For example, ferrite and pearlite are relatively soft microstructures with good ductility. Martensite is initially formed upon cooling and is relatively hard and brittle with low ductility. For most applications, it is desirable to maximize the amount of martensite that has been formed and to minimize the amount of pearlite. This is done by cooling the steel sufficiently fast enough to maximize the formation of martensite. Using a continuous cooling transformation curve, or CCT curve, for the steel of interest, the critical cooling rate that must be exceeded in order to minimize pearlite formation is the cooling rate just to the left of the nose of the pearlite transformation portion of the CCT curve. One of the most important and least understood operations in heat treating is quenching. Quenching refers to taking metal that has been heated to the hardening temperature, then cooling it to a lower temperature in such a way as to maximize the formation of the desired microstructure, usually martensite, which will produce the necessary hardness, strength, and toughness. It should be noted that martensite occupies a larger unit volume than austenite and the other microstructures formed from austenite. Such dimensional changes during heating and cooling have been measured and are illustrated by this curve. Here we see the steel decreases in size with cooling, which is expected, until martensite is formed. At this time, there is a corresponding increase in the dimensions of steel due to the large crystalline lattice structure of martensite. This dimensional expansion is one of the main reasons for distortion and cracking. Therefore, the transformation of martensite from austenite is accompanied by a volumetric expansion of the steel, creating what is called transformational stress in the steel. Sometimes the transformational stress may be sufficient to cause the steel to crack. The challenge of engineering an optimal quenching process is to cool the steel sufficiently fast to maximize the formation of martensite, while at the same time minimizing the potential for unacceptable distortion and cracking. The formation of the desired microstructure is dependent on the alloy, the dimension of the treated part, and the quenchant selected. Let's first look at the effect on a steel alloy. Here we see a simplified transformation diagram for a plain carbon AISI 1045 steel. Now let's compare a simplified transformation diagram for AISI 4140 steel. Notice that the nose of the pearlite transformation is farther to the left for the 1045 steel than for the 4140. This means that it is easier to avoid pearlite transformation products from 4140 than for 1045 steel. In other words, the higher alloy content of the 4140 steel makes it more hardenable than the 1045 steel. This is why we say that the 4140 has a higher hardenability than the 1045. This is confirmed by comparing the hardness obtained when identical pieces of 1045 and 4140 steel are immersed in a given quench oil. The ability to through-harden steel is not only dependent on the hardenability of the steel, but is also dependent on the dimensions of the component and the quenchant selected. For example, cold water or brine, which are fast quenchants, are often selected for more difficult to harden plain carbon steels in order to maximize the formation of the desired martensite microstructure. If hot water is selected, the formation of undesirable pearlite in addition to the formation of martensite will be possible. If the steel is simply placed in air and allowed to cool, the desired martensite will not be formed. Instead, a pearlitic structure will be formed which has a low hardness and strength. Other quenchants, such as fast oils or slow quench oils, will produce different cooling rates, which will also affect the steel's ability to achieve the desired microstructure during the quenching process. Therefore, it is important to select the right quenchant to properly harden steel. The ability to harden steel is actually dependent on many factors. These include hardenability, the inherent ability to harden the steel or the steel alloy selected, cross-section size, quenchant, quenchant temperature, quenchant flow rate by the part, concentration of polymer, and charging pattern or load density. The quenching process has long been known as the black hole of heat treating for very practical reason. You cannot see what is happening during the quench once the parts are loaded into the tank. However, once the parts are removed, you may see severely distorted or cracked parts, or you may obtain parts that are too soft or perhaps even non-uniform or spotty hardness. What causes these conditions? Let's first look at what happens when hot metal is immersed into cold water. Although the quenching process is very fast, a slow motion sequence shows that there are 3 cooling processes occurring. Upon initial immersion, the hot metal is surrounded by a vapor film. Since heat transfer is very slow in a gas, cooling rates are very low. Upon further cooling, the vapor film is ruptured and the boiling occurs, which exhibits the fastest cooling rates of the process. After further cooling, boiling stops and convective cooling occurs, which is also a slow cooling process. Perhaps most notable is that through much of the quenching process, all 3 cooling processes are occurring on the part simultaneously. This will produce non-uniform cooling with large temperature gradients, which, in turn, may lead to excessive distortion and perhaps even cracking. Now let's immerse the hot metal in a quench oil. Although the quenching is slower than observed for water, the same 3 cooling mechanisms, vapor phase, followed by a boiling phase, and then convective cooling occurs. Also, all 3 cooling mechanisms may occur simultaneous on the metal surface. Another increasingly common quenchant is a solution of an aqueous polymer. When the same metal is quenched into a polyalkyl glycol or PAG polymer quench, a different cooling process is observed. Upon initial immersion, the metal surface is covered by a polymer film which is separated from the hot metal surface by a vapor barrier. Upon cooling, the polymer film is ruptured. The boiling starts, which is then followed by a convective cooling process. We should note that the cooling process can sometimes be more uniform in areas of cooling if different mechanisms are avoided. The formation of thermal gradients that occur during quenching of an austenitic stainless steel have been studied and modeled in real time. Austenitic stainless steel was used since it does not form martensite upon cooling. This allows us to study thermal gradient and the subsequent formation of residual stresses that may be formed without the accompanying transformational stresses due to martensite formation. In this experiment, a cylindrical probe with a center thermocouple was immersed into an oil quenchant, and a cooling time temperature curve was obtained similar to the process shown here. The thermal gradients that are formed during this quenching process are shown in real time here. This improvement in cooling uniformity will reduce thermal gradients and, if proper quenching conditions are used, also reduce the potential for excessive distortion and cracking. These examples illustrate one of the most important principles in quenching. Quenching is a surface phenomenon. Cooling is controlled by the viscosity of the fluid and the thickness of the fluid film at the cooling metal surface. Less viscous fluids like water cool faster than more viscous fluids like oil. The layer thickness of a quenchant surrounding the metal, in the case of a polymer, will also affect cooling rates. Higher polymer concentrations will increase the thickness of the insulating polymer film, which will further reduce cooling rates. Therefore, anything that affects the formation and breakage, thickness, and uniformity of the quenchant at the cooling metal surface will affect the overall cooling process. Some commonly encountered problems that often lead to loss of distortion control or cracking include water contamination of the quench oil contamination of a polymer quenchant, inherent non-uniformity of a water quench, excessive foaming, non-uniform fluid flow around the part surface, oxidation of oils, thermal degradation of oil and polymers, charge pattern, not enough space between parts in the quenchant, contamination, non-uniform agitation, improper bath temperature, improper polymer concentration. Some of the most common variables that must be considered in quench processing include agitation rate, bath temperature, and concentration of a polymer quenchant. The impact of these variables can be easily illustrated from the Grossman H factor contour plot. In this figure, it is shown that increasing the agitation rate from 50 feet per minute to 75 feet per minute to 100 feet per minute increases the Grossman quench severity factor. The increasing Grossman numbers mean faster cooling. This has practical significance since all quench tanks have significant fluid flow gradients surrounding the parts during the quench, which may produce significant hardness gradients. It is important to understand that quenchant flow is an important variable for every type of quenchant, including gas, water, oil, polymer, molten salt, and others. This is illustrated by comparing the effect of agitation on the hardness of AISI 1045 steel when quenched in a fast oil. As expected, hardness improves with increasing agitation. Fluid flow variation in tanks may lead to variations in hardness, increased distortion, and possibly even cracking. Now returning back to the PAG polymer quenchant contour plot, let's look at the effect of bath temperature. This plot shows that increasing bath temperature will decrease quench severity. This is important in practice for two reasons. One is that it is important to control the initial immersion temperature and temperature rise, since it will affect the cooling rates throughout the quenching process and thus the ability to obtain uniform as-quenched product. A temperature rise during quenching in oil is not so critical, as quenching severity in oil is less affected by temperature. The second reason is that thermal gradients around the part will greatly increase the potential for increased distortion or cracking. For polymer quenchants, the effect of quenchant concentration is also important. This plot shows that increasing quenchant concentration will decrease quench severity. This is reasonable since high polymer concentrations provide greater insulating film thickness and slower cooling rates. Cross-section size also is an important consideration. Generally, increasing the cross-section size decreases the quench rate, thus producing softer parts, all other variables being equal. This is illustrated in this diagram when cooling curves for a 10% polymer quenchant at 32 degrees Celsius, 90 degrees Fahrenheit are superimposed on a transformation diagram for AISI 1045 steel. And also for cooling curves for a 20% concentration of a polymer quenchant at 60 degrees Celsius, 140 degrees Fahrenheit, superimposed on a transformation diagram for AISI 4140 steel. In both cases, hardness decreases as cross-section sizes of the bar increases from 1/2 to 1 to 1 1/2 to 2 inches. In addition to cross-section size, the shape of the component being quenched must also be considered. For example, compare the uniformity of film breakage and direction of nucleate boiling at the front of the solid cylinder, a disc, a gear, and a hollow cylinder. In each case, the shape of the part can affect fluid flow over and around the cooling surface. One of the most difficult to quench configurations is the long tube, where vapor can become entrapped inside of the tube. This means that cooling on the outside surface will be much greater than on the inside surface, and the cooling mechanism along the length of the tube will be non-uniform, leading to very large thermal gradients and very bad distortion problems. This has been addressed in practice by immersing the tube stock into the quenchant at an angle or vertically. Both methods facilitate release of the vapor from the inside of the tube, promoting at least somewhat greater uniformity throughout the quench, thus reducing distortion. Let's take a look at quench system design. The three types of systems we will discuss are batch quench systems, continuous quench systems, induction open, and submerged spray systems. We will begin with a discussion of batch quench systems. These systems include open tanks, pit quench systems, and integral quench systems. One of the most common quench systems is the open tank. Properly designed open tank systems will employ either a pump, impeller, or spray agitation, or a combination of all three if optimal quench uniformity is to be achieved. Of these, the most common agitation is impeller agitation. There are numerous designs possible, which depends on the configuration of the load being quenched, size and depth of the tank, the quenchant being used, and other factors. In many cases, The impeller is encased in a tube which acts as a pump with the potential for directional control. These arrangements are called draft tubes. For example, multiple draft tube agitation is used for this elevator quench system. Another common configuration is the pit quench. A pit quench system often utilizes a draft tube agitator, such as this one. Perhaps the most common quench system in the entire industry is the integral quench, also known as a sealed quench system. In these systems, the quench tank is attached to the furnace, which is separated by an inner door seal. There are many integral quench tank agitation arrangements, which include open and draft tube impeller stirrers. There are some common design recommendations for integral quench batch systems. The total workload, including the weight of the fixtures, should not exceed 1 pound of metal to 1 gallon of quenchant. The temperature rise of the quenchant during the quench should not exceed 10 degrees Celsius, 50 degrees Fahrenheit for polymers, and 40 degrees Celsius, 104 degrees Fahrenheit for oils. Racking of the parts should facilitate an upwards quenchant flow through the load. There should be a tight inner door seal to prevent quenchant vapor from entering the furnace. It is recommended that a slight positive pressure in the furnace be provided during the transfer of the load into the quench chamber during the quench. The agitators must always be on when the inner door is open to minimize vapor buildup in the quench chamber. This is especially important when polymer quenchants are used. Many heat treat processes employ continuous furnace designs where the parts to be heat treated are loaded on a belt, which then pass through the furnace and then drops from the belt through a chute zone into the quenchant. The parts are then removed from the quench tank using another belt and run onto the receiving line or basket. Numerous chute quench systems have been designed. Some of those are illustrated here. The best designs provide openings, preferably screened, to allow the heated quenchant to escape the quench zone. Optimal countercurrent quenchant flow around the part to facilitate uniform heat transfer as the part is dropping through the chute zone. A cooling jacket above the quench zone to prevent oil or water vapor from entering the furnace. A fuming ductor located in the chute area above the cooling jacket to provide further insurance against quenchant vapor contamination of the furnace atmosphere. A mesh belt of sufficient porosity and length to allow for quenchant agitation around the part to facilitate completion of the quench before removal from the tank. Although there are induction heat treating processes which employ a manual dunk and agitation as shown here, most processes employ either an open or submerged spray. In all cases, it is important that the quenchant reservoir be large enough to allow the foam head to be drawn back into the system. If the reservoir is too small, the part will be quenched with a mixture of foam and water, which will lead to an increase in distortion as well as a decrease in hardness. Typically, it is recommended that the volume of the reservoir be 5 to 8 times the volume rate of flow. For example, if the flow rate is 10 gallons per minute, then the reservoir should be at least 50 to 80 gallons. Another problem often encountered with polymer quenchants used in induction systems is that excessive pressures are used which effectively blow the polymer film off the part prematurely and non-uniformly, which also leads to poor distortion control. In this presentation, a brief review of steel hardenability and its effect on quenchant selection was discussed. The effect of various quenching process variables on quench severity were reviewed. These include bath temperature, agitation, and for polymer quenchants, concentration. In general, increasing agitation increases quench severity, increasing bath temperature decreases quench severity, and increasing concentration decreases quench severity. The effect of cross-section size on the ability to through-harden steel was illustrated. The effect of part shape on the uniformity of the quenching process was also illustrated. An overview of a number of industrial quenchant systems, including batch, continuous, and spray systems used for induction hardening was provided. However, of the various subjects reviewed, perhaps the most important is the necessity of optimizing the uniformity of the quenching process to reduce thermal gradients, which may subsequently lead to problems with distortion control. A number of common contributors to non-uniform quenching were provided. With this understanding, the black hole of heat treating will no longer be a mystery.